Namaste. As we got familiarity with the calculation of inductance for composite conductors, as well as we have done it for single phase circuits, now we will move on to the three phase circuits. Okay, in this learning dialogue video, we are going to discuss about how to calculate the inductance for a three phase circuit. Okay, let us consider the simple three phase line. Okay, it's and here the important thing what you need to understand is here we are considering an unsymmetrically spaced three phase line. Just if you look at the distances between the conductors A, B and C, they are not equal. Okay? Which is true in the real time scenario. Okay? If you have observed the way in which these transmission lines are located while you are traveling across the cities or that in your own town, you might have observed that they are hanged one below the other in most of the cases in case of transmission lines. Okay, I'm not discussing about the distribution lines which you will normally come across in your streets. Okay, they will be hanged in the horizontal way, but if you look at the transmission line network configurations, normally they are placed one below the other. Okay, even in such case also, the distance between the conductors, they are not equal. Let us say conductor A is in the top and conductor B is in the middle and the conductor C is in the below. Okay, so the distance between conductor A and B could be some capital D distance, D meters, and if you take B and C, again it is you can assume it as equal as D meters. But if you look at the distance between A and C, that is not equal. Okay, that is going to be 2D. Okay, so normal scenario is the lines are unsymmetrically spaced. Okay, so here also we are considering the same scenario, that is unsymmetrically spaced conductors. Okay, so this is the cross-sectional view of a three-phase line with unsymmetrical spacing. So you have three conductors A, B, C. The distances are between A and B it is D12, and between B and C it is D23, and between A and C it is D31. Okay. So now let us try to calculate the inductance for such a three-phase line. Okay. So before we'll try to use our uh, flex linkages and other things to calculate the inductance. Just if you look at this unsymmetry in the spacing, one of the problem with this unsymmetry is the flux linked with these conductors is completely unsymmetrical. Okay, so that it's not even. Okay, it's not uniform for all the three conductors. So obviously there will be a difference in the inductance of these three conductors A, B, and C. Okay, so even though you apply the same amount of voltage with the same magnitude from sending in, if you apply a balanced voltage across all these three conductors, by the time you observe the voltage at the receiving end, at the other end, then what are the voltages that are measured at the secondary or receiving end? They are not symmetrical, they are unsymmetrical. Okay, so that is because of the unsymmetrical spacing among the three conductors in the three-phase line. So how to handle this problem? Okay, but in the real time, if you get unsymmetrical unbalanced voltage at the receiving end, obviously that will create a lot of problems with the load. Okay, for example, if you take your induction motors, which are the workhorses of your industry, what happens? Okay, if they are subjected to unbalanced voltages, okay, the rotors will get heated up, okay, because of this unbalanced voltage. Okay, likewise, you will have several problems with this unbalanced voltage in the receiving end. Though the voltage which are given at the sending end, they are balanced. By the time they reach the receiving end, they will become unbalanced because of this unsymmetrical spacing, which causes the even flux linkages with the three conductors. That's going to create an unbalance the receiving end voltage. So to overcome this, what we'll do is we'll make use of a simple technique. For every 100 kilometers or 100 meters, what will normally it will be more than meters. Okay, so what we'll do is we will transpose the positions of the conductors. Here, if you look at this particular configuration, you have A, on the left hand bottom, and the B on the top, and the C on the right hand side. Okay, so now what we'll do is we'll have the transmission lines which are hang or a distance in this configuration, and after a certain distance what we'll do is we'll interchange the positions. Now we'll move A to B and B to C and C to A. So if you consider the this configuration ABC as the first section, by the time it reaches the second section, it will become CAB, CAB. Okay, and then again after the same distance, what we'll do is we will again change the positions of these three conductors. So if you look at the configuration of this uh, lines, okay, this is what I have already explained. Okay, I am going to show you this configuration. Yeah, at equal distances we'll try to change the positions of conductors A, B, C. Okay, so you can divide this entire picture into three sections. This is first section, this is second section, and this is third section. Okay, this is third section. Okay, this is second section, and this is your first section. Okay, in the first section you have your A conductor in position 1 and B conductor in position 2 and C conductor in position 3. Okay, now when you move on to the second section, okay, A, which is in position 1, got moved to position 2, this position 2. Okay, A, now it's in position 2. Okay, and B, which is in position 2 in first section, has moved to position 3 in section 2. Okay, so similarly the C, which is in position 3 in first section, now it has moved to position 1 in section 2. Okay, so again after the same distance, what we'll do is we'll again change. Okay, so what are the A, which is in position 2 in section 2, will now move to position 3 in section 3. And similarly, the B, which is 1 in section 3. And whereas the conductor C, which is in position 1 in section 2, will move to position 2 in section 3. Okay, so likewise, at equal intervals of distance, we will interchange the positions of these conductors. Okay, A got moved from position A to position 2 and position 3. Okay, by the time it completes one cycle, and this particular cycle is called, consisting of these three sections, it is called a transposition cycle. Transposition cycle, where a particular conductor will take the positions of the remaining two conductors. Okay, so B is in position 2 in first section. By the time it goes to the section 2, it moved to 3 and then again 1. So it occupies all the three positions in each cycle. Cycle is called transposition cycle. So over the length of one transposition cycle, the total flux linkages and hence the net voltage induced in the nearby telephone line is 0. So since there is interchange of these positions, what are the flux link? If you take the average and the voltage that are induced because of these flux linkages in the neighboring telephone lines, that will become 0. Okay, so that is the advantage of using transposition. Okay, so how to change the positions of these conductors, and where do we change the positions? Because if you look at your transmission towers, you cannot simply change the positions on the transmission towers. Okay, if you try to do, there will be some snapping across the conductors also. That may also be possible. Okay, so what we'll do is normally we'll prefer to change these positions at the substation level. Okay, and obviously these substations may not be at the same distance, so that maybe so there may be some differences in the distances, and again we may not achieve the exact zero voltage that is induced in the telephone lines, nearby telephone lines, because this transposition cycle because it's practically not possible to have uniform intervals of distances to interchange the positions of these uh, lines. Okay, so that is one of the challenges in transposition of these transmission lines. Okay, this is about transposition cycle in case of inductance measurement. Okay. We'll continue the measurement of inductance of three-phase lines in the next learning dialog video.